So we are the next functional group to talk about are carboxylic acids. And then we do carboxylic acid derivatives, and then we have one more chapter after that. So it's going to be tight to finish all of this without going into hyperspeed. And trust me, I know what student comments are on that. Long time ago, I was walking up the hallway, and a student said, and I don't dispute this, well, if they just would have gone faster at the beginning, then they wouldn't have to cram all this stuff in at the end. True statement. But we're not going to necessarily go into hyperspeed, but we'll hit the major, sort of the major fundamental issues. So with carboxylic acids, if you look at, if I pull up top hats, the topics, the first thing is naming carboxylic acids, and there is a whole common name as well as commercial sources of carboxylic acids. You can go ahead and read that on your own. The synthesis of the carboxylic acids are things that we've done before. So I could, but this is Monday morning, so it's going to be awfully tough on everybody if I said, oh, oxidation of aldehydes and primary alcohols. And I said, what kind of reagent do we use to oxidize a primary alcohol or an aldehyde to a carboxylic acid? And you would say, David, KMNO4, what else? Heat with an oxidizing reagent. So KMNO4 will work. What else? The whole suite of them, Aisha. Any chromium 6, so K2, CR2O7, CR03, any of those? What would not work? There's a whole suite of those reagents. Katie? PCC will not oxidize to a carboxylic acid. PCC. Swern. Des-Martin. Any of those reagents that oxidize to the aldehyde will not work. So, okay, so we kind of know that one. Oxidation of alkynes to give carboxylic acids. So in other words, if I have an alkyne and I would like to cleave it, and it doesn't matter whether it's a terminal alkyne or an internal alkyne, if I cleave an alkyne, I'm going to get carboxylic acids. What kind of reagent would I use there? Bless you. It's an oxidizing reagent. Got to be a strong oxidizing reagent. Reducing reagent. I want the opposite. So I want a really strong oxidizing reagent that we've already said this morning. David? KMNO4, chromium 6, the really strong ones. Anything with a chromium 6 plus in it, those will cleave the triple bond and make a carboxylic acid. Of course, I don't know why they said triple bonds, because couldn't I do the same thing with a double bond and cleave it to make carboxylic acids? Yes, I could. What reagent would I use there? Hint, strong oxidizers. KMnO4, chromium 6. Although, there is also, what else could I do to the double bond to cleave it and make a carboxylic acid? I could do, and it starts with O. I could do ozonolysis. So I could use O3 and H2O2 to cleave that double bond and make carboxylic acids out of it. So I'm sure they put that in there as well. So again, these are just all the different ways that we can make carboxylic acids. A review. All right, what else do they have? They've got oxidation of alkyl benzenes. So take an alkyl benzene and treat it with what to give a carboxylic acid? It's already on the slide. KMnO4. I guess when in doubt, KMnO4. All right, so we can oxidize alkyl benzenes, and then we'll talk about hydrolysis of nitriles and all of the other what are called carboxylic acid derivatives, but we have talked about that. Carboxylation of Grignard reagents. So we take a Grignard, and what do we add to that to make a carboxylic acid? So if I have a Grignard and I want to make the carboxylic acid out of it, what should I add? Colin? CO2 and then H+. So we can do that. What else? And then the reaction of carboxylic acids with nucleophilic acyl substitution. We're gonna get to that. Okay, so that means in chapter 24, and when I put the amine chapter up, there's 4 questions in the amine chapter. So I think I said I would make the amine chapter due by next Wednesday. There's 4 questions. Okay, so that shouldn't be too taxing. But the problems that we're doing today, there were a little bit more. All right, so now what we can, so that's our review of substitution of carboxylic acids. And you'll have to do that as you go through these problems. I'm going to try and make sure that everything's not due like on the last day of class, but it's going to be pretty close. So if you get your problems for today done and you get all 4 of the amine problems done, you can always start on the carboxylic acid problems, because we've talked about all of this. And I don't know how many problems there are there, but probably between 5 and 20. Okay, so now let's talk about reactions of carboxylic acids. And in terms of reactions of carboxylic acids, we can start with that reaction, which is called what kind of esterification? There's a name associated with it.
Fischer?
That's Fischer esterification. I believe the same Fisher that came up with Fisher projections. So Fisher esterification is when we take a carboxylic acid, react it with an alcohol with acid as our catalyst. So we should probably go through the mechanism of this, although, well, we should, because you're going to have to do this, at least those of you who are in Dr. Simmons and my labs, and had to go through it for the benzocaine. But if I'm going to react the carboxylic acid with the like sulfuric acid catalyst, what's the first step? Which oxygen? The carbonyl oxygen. So I'm actually going to protonate the carbonyl oxygen. If I remember, I'll come back and show you why you cannot protonate the other one. So that's going to give us then our oxonium ion. And what happens next? Let's get some more people involved here. I didn't bring the wheel. Let's see, how can I do this with the dice? How many tables we got? 1, 2, 3, 4, 5 tables times. We got 20 tables. Okay, we got 20 tables. Then let's go ahead and okay, table 19. That's Patrick, that's you and Jacob. Okay, so you want to write the resonance structure, which we can do. So we're going to write the resonance structure. And then what happens next, Patrick? Patrick. Okay. So we're going to take the alcohol and we're going to attack the carbonyl. What was a carbonyl carbon? Okay. Okay, what happens next? Table 18. You're all by yourself. Okay, so lose this hydrogen. Okay. So I'm going to lose the H plus. Okay. What happens next? Let's see, table 16. So that's you, Lexi. You have free H plus floating around. So you got free H. We just lost an H plus, so we have an H plus to protonate something. So in that molecule, what do you want to protonate? Which one? Does it matter? It's not going to matter. So we'll go ahead and protonate the top H+. Okay, so that will then give us an oxonium ion. And what would have happened if we would have protonated the OR group? It just would have gone backwards. So we protonate either one of the OH groups. Okay, so then what happens next? Table 7. 5, 6, 7. The water leaves. Agreed. Okay. So the water is going to leave. We're going to go to a next slide. Okay, so we got that carbocation. And that carbocation actually has a couple of resonance structures you can draw for it. If you were to take the lone pair off either the OH or the OR, you could form a double bond. So this wall doesn't look like it's very stable. It actually is because it's got two more resonance structures. Okay, so now we're ready for the final step, table 11, which is David.
The H on the alcohol and then the double bond.
Okay, so I'm going to lose my H+, regenerating my catalyst to now form the ester. So we're gonna do these carboxylic acid and acid derivative mechanisms here, and they're all pretty much the same. A lot of them involve acid, and so you protonate something, it leaves, something attacks, and so this is, and there's different variations on this. So for instance, if I go back, sometimes you'll see people bring this pair of electrons here and then kick the water off. And I would accept that because that's used a lot in books, and I don't know if I believe whether that really occurs or not. And I haven't searched the literature to find out whether it does. But that you can combine those last couple steps into that. That would be okay. And actually, I think that was what was on the esterification handout that those of you got. Okay, so that's the mechanism for Fischer esterification. Now, what people did mechanistically to determine that that was actually the case was they took a carboxylic acid and they added to it an alcohol where oxygen comes in three isotopes. It comes in oxygen 16, which is the biggest, oxygen 17, and oxygen 18. Oxygen 18 is radioactive, and so what they did was they actually took an oxygen 18 labeled alcohol, and when they performed that reaction, they found that the oxygen 18 was the one incorporated in the ester. And so that's how they knew that there was no other oxygen that was present at that point. So that's how you can use isotopes here to determine that that is really the mechanism, or it's consistent with the mechanism. Now, I said if I remembered why isn't the other oxygen in a carboxylic acid acidic or basic? Why won't it pick up a proton? I can draw two resonance structures for a carboxylic acid. I could take this pair of electrons, move here. So here is the other possible resonance structure for a carboxylic acid with a +1 charge and a -1 charge on the oxygen. Now you might say, not very stable resonance structure, but it is another valid resonance structure. So the resonance hybrid for this would look like this. We would have a delta minus charge on the carbonyl oxygen, and we would have a delta plus charge on the oxygen attached to the hydrogen. So there is a little bit of a positive charge on that oxygen, which means that if I'm going to add H+, I'm going to add H+ exclusively to the carbonyl oxygen, because that oxygen's not going to want to bond at H+. Okay. So whenever we protonate a carboxylic acid or an ester, we always protonate the carboxylic or the carbonyl oxygen. We never protonate the OR or the OH, because it's already got some positive charge on it. So that's Fischer esterification in terms of making esters. Now there's other ways to make esters out of carboxylic acids. I could say, okay, I want to convert my carboxylic acid to an acid chloride and then react the alcohol with it. And if I do that, I form the ester, and there's no equilibrium. The problem with Fischer esterification is there's an equilibrium between the acid and alcohol and the final ester. We normally drive, and I'll just rewrite that. So typical Fischer esterification is an equilibrium process. And so the only way to push that equilibrium in the Fischer esterification is to use one of the reagents in excess. If we used one of them in excess, we would probably use the carboxylic acid in excess, because then at the end of the process we could use sodium bicarbonate to extract it into the aqueous layer. But that's the issue with Fischer esterification, is overcoming that equilibrium. If you convert the carboxylic acid to a carboxylic acid chloride and then react it with alcohol, it's a 100% reaction. The only thing I need to know is, how do I convert the carboxylic acid to the acid chloride? So I need to know what reagent goes here. Katie? SOCl2 or PCl3 or PCl5, any of those reagents. Because what is their goal or their function? To turn an OH into a Cl. So that's another way to make an ester. It's also possible, I saw many people do this on the exam, is to take and react the carboxylic acid with a base to form a carboxylate, and then react it with an alkyl halide Typically, it has to be a primary alkyl halide. And it would be even best if it was a methyl group, so that you could do an SN2 reaction. And so in this case, you would need the appropriate base to deprotonate the carboxylic acid. Give me a base. Here. Overkill, but yes. Give me another base. Overkill, but yes. C minus, definite overkill, but yes, it would work. H minus would also work. Sodium hydroxide, now we're getting more realistic. And what else? What base did I just mention? I think I mentioned it. Because carboxylic acids are fairly strong acids, so it doesn't take a really super strong base to do this. How about bicarbonate? Right? That's why when you were extracting, you couldn't just throw in the sodium bicarbonate, put the stopper on it, and start shaking wildly, because you were going to generate CO2 because it was going to react with the carboxylic acid. So carboxylic acid can be deprotonated by any of those. But you can do these, you can do this SN2 reaction. That's okay. It's allowed. But you're really limited here by the type of alkyl halide. It's really got to be primary. And it would be best if it was like methyl iodide. And methyl iodide, methyl chloride, methyl bromide. The problem with these reagents are that they are, they're not really good to use. Because if they were to get on your skin or somehow you get them in your body, they are great electrophiles and they just start methylating stuff. And you don't want to methylate DNA or RNA or enzymes. I mean, that leads to mutation, usually not in a good way, right? You don't get any kind of superpowers out of that. You just get disease. So that's not a great reagent to use, but it could be used. Now, to make methyl esters, you could do this, but there's actually a slightly different method that's been used, and that's using what's called diazomethane. And with diazomethane, what you do is you react the carboxylic acid with diazomethane, which is CH2N. So if we look at that, it would probably have two double bonds here for it to be neutral, because this is -1. The center nitrogen, if you kind of take anything away from this here, whenever you have a center nitrogen with two double bonds, it's always +1 in its formal charge. And then the carbon is 0. But what we can actually do is we can actually rearrange this molecule. So basically what's going to happen is that your oxygen here is going to come in and add to the carbon, and actually the hydrogen is going to add as well. And then, of course, you're going to end up with this group leaving as N2 gas. And so what you end up doing is you end up methylating your carboxylic acid to make a methyl ester with diazomethane. Okay. And they go through the exact mechanism in Top Hat. I'm not going to go into that. The problem with this reaction is that, I mean, it's very nice to make methyl esters, but the problem is that you have to generate the diazomethane in situ, which means that basically you have to generate the diazomethane gas and then bubble it into the reaction, because making diazomethane itself, it's unstable because it has that embedded gas molecule in it. So you end up having to make the diazomethane and then react it. And there's a whole dedicated glassware to be able to do that. So this is another way to make a methyl ester. It's very specialized, and it's very old in terms of historic, but it is another way to make a methyl ester. So we can take carboxylic acids and we can make esters out of them. And we've also seen that we can take our carboxylic acid and we can convert our carboxylic acid into an acid chloride. So what else can we do with the carboxylic acid? Let's react the carboxylic acid with carboxylic acid chloride. What do you think will happen here? What do you think the first step of the mechanism should be? No acid present.
Is it that the H and the Cl are going to come together and then it's going to join those two?
That is true. I'm going to end up forming carboxylic. I'm going to end up forming HCl, and I'm going to end up making that molecule. Does anybody know the name of that molecule? That's a carboxylic acid anhydride. In our benzocaine synthesis, we reacted acetic anhydride with the NH2 of the original molecule to make the amide. So, in this case, that's what will happen. I can also make an anhydride by reacting two equivalents of carboxylic acid together in the presence of something like sulfuric acid. So that's what will happen. The question is, can we think about the mechanism for this? And so the acid chloride, if I do the acid chloride mechanism, what's going to happen? Now, we've reacted acid chlorides before. So let's say I take my carboxylic acid the OH is going to attack the carbonyl. So I'm going to make that. And then what do you think happens next? Table 5. 1, 2, 3, 4, 5. Okay, I'll lose the H, and where do you think it's going to go? Go to the O minus? So one of the things that could happen is we could end up just transferring the hydrogen so that I end up with this. And so now in the last step, remember I want to make an anhydride. In the last step, what should happen? Table 10. Your hint is chlorine's a good leaving group. And at the same time, do what? That. So in other words, I'm going to lose HCl here, and that's going to give me the final product. So we've seen this mechanism. We've seen this mechanism with Grignards. When we added 2 equivalents of Grignard to an acid chloride, we would lose the chloride. And we're going to see this mechanism over and over and over again when we do the derivatives, which I'm kind of mixing in here. So that when we get to them, I'll say, hey, remember when we did this? And of course, you'll look at me like, no, I don't remember that. But we're not into the last 2 weeks, are we? Because then in the last 2 weeks, I'm supposed to understand that you're done in the last 2 weeks. When I got here in my first year, which is now 25 years ago, and trust me, it hasn't gone by very quickly at times. But when I got here, Dr. Weaver told me, he said, well, he goes, last 2 weeks, they really won't listen to you. Now, I was at OU. I was used to students not listening to me from like day one. So that was, I got that. But I'm like, really? The last 2 weeks? And he goes, well, you know, everybody's tired. And, you know, I understand, but we really have to just keep moving forward. Do not, if you have senioritis, get rid of it until you're done with your last final. If you think you have senioritis and you're not a senior, get rid of that until you're a senior. But again, we want to keep going until we're done with our last final. Jacob? Okay, so we're still away from 2 weeks. So if you started the 2 weeks early, get refreshed over break. Well, that's why we give the test on the second to last week. Okay, but we've done this before. You attack the carbonyl, pair of electrons comes back down, kicks something out. We're going to do this so many times. It's just, that's how these reactions occur. All right, so that's what happens if I take a carboxylic acid and react it with a chloride. I can make the anhydride. What else can I do? Well, other reactions of carboxylic acids. There are organolithium reagents, which are the equivalent of Grignards. There's also then an R minus and an H minus. So if I take my carboxylic acid and I react it with lithium aluminum hydride, what am I going to make? There'll then be an then H plus H2O step. So lithium aluminum hydride is a reducing reagent. carboxylic acids get reduced down to what? Katie? What kind of alcohol? The primary alcohol. So I'm going to reduce this all the way down to the primary alcohol. Now, the mechanism has a little magic in it. It's really not, but it's something that's kind of new. But before we do that, lithium aluminum hydride has 4 H minuses in it. Okay? So we have to remember that. Lithium and sodium borohydride have up to 4 H minuses. So let me ask, if I'm going to work towards this mechanism, I'm going to react the carboxylic acid with 1 H minus. What am I going to get? It's going to deprotonate it. And fortunately, we just talked about that. Well, you gave me suggestions on bases to deprotonate carboxylic acids, and one of the ones that I said was kind of overkill is H minus. So the first equivalent of H minus is going to deprotonate it. Then what's the second equivalent of H minus going to do? What's been the general theme of nucleophile carbonyl group? What's the H minus going to do to the carbonyl group? Add or attack it. Yes.
Does that carbon have a slight positive charge
Yes.
due to resonance?
No, just due to the fact that the 2 O minuses are pulling out electron density from it. So at this point, I have a hydrate that's been double deprotonated. Okay. But in order for me to get all the way back down to the primary alcohol, what I have to do is I have to now pay attention to what happened to the lithium aluminum hydride. Normally, I don't care about it. I have to. So I got a lithium plus. Okay, there's a counter ion to that O minus. My AlH4 minus now just lost 2 H minuses. 1 deprotonating, 2 adding. So that means that AlH4 is now an AlH2 with a plus charge. And that now becomes a counter ion on the second oxygen. As a matter of fact, that oxygen aluminum bond isn't just a minus plus 1. It's a bond. And now I've got my H down here. All right, so what can happen here? Well, what can happen is this pair of electrons can move here, and that pair of electrons can go to the oxygen. So that now I basically have a leaving group. So now I form an aldehyde and I've got lithium plus and an O with an ALH2 on it. So that O with the aluminum basically becomes a leaving group. I haven't added acid yet. I have my aldehyde. My lithium aluminum hydride had up to 4 H minuses. I've used 2. H minus number 3 now comes in and adds to the aldehyde to now form a primary alkoxide. Can the O minus do anything? That's probably off with the lithium, or there's probably a lithium here, but I'm done worrying about it. Once it gives up the third H minus, I'm now at this. That O minus cannot form a double bond because there's no leaving groups. So it waits now for what to happen? For me to add H plus H2O. So now when I add my H plus H2O, what do I get? My primary alcohol. So that aluminum counterion is sort of the magic in this reaction. It's how we basically lose one of the oxygens that allows us to go back down to the primary alcohol. Okay. So that's the mechanism for the reduction of the carboxylic acid. And with this carboxylic acid now, I can do some different things. And I'll come back to this one. I'll come back to that intermediate on Wednesday, because if I protonated at that point, I would end up with a hydrate. Hydrates are unstable, and that hydrate would have gone all the way back to the aldehyde. And if I did a Grignard, where that H would now be an R group, it would go all the way back to a ketone. So we have to remember back with our hydrates and our acetals and all of those things, because we're going to start making them. Okay, so I have your homework problems up here if you want to come up and get them. If not, you can get them on Wednesday or you can stop by. They are in alphabetical order today, so Sarmand, Abby. I did take a quick look at them. So I would check them over. Nicole, Josie, Sarah. I'm not going anywhere, so you're going to have to come to me. Nicole, Ben, you want yours? Ashton's not here. Sydney, Lexi.
Can I
Leah.
bring you my homework in like 20 minutes to your office? I just have to rewrite it.
Okay. Patrick, Kristen, Leah, Patrick,
There you go.
Benjamin.
This is mine too.
Okay. Yeah, if you have your problems from Friday, you can give those to me. I haven't posted the answer key yet. Shelby, Nicole, Nicole, Shelby, Haley, Michael, Joe, Carolyn, Aisha, Taylor, Katie, Lucy, Lauren, Krista, Hannah, Hope, Carly, Maddie, already left, David, Olivia,
Thank you.
Amy,
Sorry I
Jacob,
walked in late. I got caught in traffic this morning.
that's fine. Maddie, other Maddie,
Were you able to get the NMR?
yes, but I haven't I'm gonna take your samples this morning. So I will take, I was able to get the NMR to work on Friday, but I was gonna take them last night, and I'm gonna take them this morning, and I'll scan them and send them to you. And I'll mark them up. So, like, if there's any alcohol in there, I'll mark it as alcohol. The only thing that'll be integrated will be ester. But you'll get them. Well, let's see if I can get back to my office without any crises happening. I'll try and do it right now. So.